I used the I did a literature review on biomedical applications of quantum dots, especially in the luciferase red quantum dot systems, in which the quantum dots are used as acceptors. What makes actually and because of the special properties showing by the quantum dots in the biomedical applications, why actually the quantum dots are showing these special properties. The first application is of protein sensing and second application is of bioimaging applications. What actually the quantum dots are. Quantum dots are nothing but the intermediate state of matter between the bulk material and the atom, and they show unique special properties which are entirely different from the bulk material as well as the atom, and they show distinct colors depending on the size and the shape. And some other properties like three-dimensional quantization, high quantum means, and long exactly like that. Here you see the quantum dot surface, on the quantum dot surface there are a lot of bioconjugation properties. The capacity of the quantum dot is so like it's a free choice of showing bioconjugation properties. Different thiols, the proteins, peptides, as my interest is in of biomedical applications. Then see what actually these all special physical properties are due to the quantum confinement. What actually the quantum confinement is? The quantum confinement is nothing but in the semiconductor, when we radiate with like electromagnetic radiation, there is a transition of electrons from the valency band to the conduction band. And during this process, there is a generation of electron-hole pair, which is called as exciton. If we consider the exciton, this box, consider a particle in a box model. If this box is a crystal and this particle is of my exciton, the electron-hole pair of the semiconductor, if we reduce the crystal size, then there is a discretization of energy levels we can see. By this discretization of energy levels, there is clearly observable energy states. There is an increase in band gap. Thus we show the characteristic properties of the quantum. Let's see how actually the quantum confinement is happening. Here you observe that on the reduction of the crystal size, the exciton there is a restricted movement of the exciton. Because of the restricted movement, there is a discretization of energy levels. Here you can see there is an increase in band gap, discretization of energy levels, and blue shift in the absorption. These are the effects of quantum confinement. And looking with my interest in chalcogenides. Even though there are various reports reported on cadmium chalcogenides, my special interest is on biomedical applications. As cadmium is more toxic compared to the zinc, I chosen the zinc chalcogenides. And the main property, like the zinc is of less toxic and it is highly biocompatible, that it can bioconjugate to the proteins, peptides that are present in our body. And my objective of the project is that the synthesis of these quantum dots through aqueous route, and also the study of various thiols as capping agents with different end groups and different chain lengths, and also to understand the role of thiols, how they're showing the difference in the optical and the surface properties, and utilized mainly in the bioimaging and biomedical applications. Let's see the synthesis of zinc telluride quantum dots by aqueous route. We prepared a series of quantum dots like zinc tellurides, zinc selenides, and then followed by alloy of that, and then manganese bromide. If we see the outline of this pathway, telluric acid is reduced with sodium borohydride in the continuous nitrogen bubbling, providing inert atmosphere, and then stored it for 8 degrees centigrade in the freezer. And after that, we can clearly see that there is a separation of supernatant and precipitate where sodium tetrachloride is contaminated thing and settling down, and the NH3 solution which we required for telluride, we are using that. If you see, this separation doesn't take place in one shot. First of all, on reducing that first, we get a black color, and then it will show purple color, and then it will show the colorless solution. Next, synthesis of zinc telluride. By this, from the supernatant, we take from the syringe, and then we add to the freshly prepared zinc solution, which is TGA tag. Here we maintain the pH 12, especially because the TGA shows good binding affinity for the surface of the zinc telluride particle, and as well as it shows good affinity for the cationic states of the zinc, and also it will show a good moderation in the nucleus and the crystal growth of the nanoparticle. And if you see the synthesis, the room, after adding all the reagents, we are getting a homogeneous black color solution, and after 7 days, it is giving a clear solution where we are precipitating centrifuges of the solution. Here, if you see that this color, this homogeneous black color solution doesn't appear in. It is a series of process. It takes almost 7 days to achieve the homogeneous black color solution. You see, after immediately adding the syringe to the NaHD solution, it is becoming a very light orange color, very pale color. After that, after 5 hours, there is observation of a dark purple color, and then after 2 days, we observed a homogeneous black color solution, and after 7th day, we observed a clear solution where we centrifuged that with 2500 of RPM, and then we preserved that solution for the UV absorption spectra and the further optical properties. And in the same way, following the same protocol, we prepared the zinc selenide and zinc telluride particles as well as the zinc selenide telluride alloy particles. In which zinc selenide we use sodium selenide, and zinc selenide telluride we take an equal molar proportions of selenide and telluride. And effect of nature of thiols. Here we are using capping agents, mainly thiols as a capping agent. Why we are using capping agent? As we know, the surface of the nanoparticles are very small, and they have the surface core atoms and the surface atoms. The surface atoms will have unsatisfied balances. To make them stabilize, we are stabilizing the nanoparticles. We are adding the thiol groups for the stability of the nanoparticles. And these are the various thiols we are using for the synthesis of chalcogenides. Mainly TGA, thioglycolic acid, cysteine, mercaptopropanic acid, histamine, and glutathione. And if we see the UV visible absorption spectra, these are the UV visible absorption profiles for the zinc selenides, tellurides with different capping agents and the alloys with different capping agents. Of this, another important thing is that we can also determine the band gap as well as the size distribution from the UV absorption spectrum. How we determine the band gap from the UV visible spectrum? If you see, for zinc telluride particularly, showing that where the peak is absorbing maximum, for that particular area, dividing the 1240 by that particular wavelength, we are doing it into converting the axis into absorption as photon energy. From this, we are doing differentiation where we get the first derivative plot, and which we are doing the next quadrant fit. And for that, where this maximum, here you can see the maximum of this derivative, the first derivative spectra is the band gap of your sample. And from this correlation, we found that the band gaps of zinc telluride, selenide, water telluride is of 3.54, 3.52, then 6.14 and 5.22. And next, correlation of band gap with the size distribution. From the first derivative plot of the absorption spectra we got, we are correlating with the particle size by exponential function of equation, which is given by Sabra and Sarma in the review paper with the parameters given. But the advantage of this best fit is that we can calculate the size of the nanocrystals by putting the parameters into this equation. From this, where the Eg versus the diameter I am showing, where the Eg is nothing but the energy band gap of the bulk zinc telluride crystal, and as well as there is the Eg bulk and the Eg nanoparticle. So for zinc telluride, it is found that the average for the bulk is 2.26, and the average size of what we got for zinc telluride is of 1.271 nanometers. And then these are following the same correlation of band gap and size distribution, we are getting these size distribution profiles for different zinc chalcogenides we have been prepared. And then size distribution was intensity. These are taken by dynamic light scattering (DLS), and these are hydrodynamic sizes, and the high quantities of water, and these are hydrodynamic sizes. But actual size can be of we can determine by TEM imaging, transmission electron microscopy techniques. And then studying the surface characterization of nanorods here, if you see the and one more contrast thing in doped and undoped zinc chalcogenides is that in doped systems, the ternary systems, the zinc manganese selenide ternary, the ternary systems are showing very bright green fluorescence, whereas in case of undoped systems, the binary systems Zn, Sc, Zn, Ta are showing a fluorescence, luminescent systems. These are the samples which make good photoluminescent signals. And going to my conclusion, we developed the doped and undoped zinc chalcogenide quantum dots where soft synthesis. And we one more thing, during first synthesis we try to reduce the hydrogen, but we are failed. But after that we are giving continuous nitrogen bubbling to make inert atmosphere and for reduction. Then we succeed in preparing this. And correlation of band gap and size with this tight binding approximation, and a good good interesting fact is observed in the photoluminescence profile of battery and cadmium conductors. And the main and as I concluded in my first presentation, my motto is to synthesize the cadmium-free conductors to make less toxic for the bio